Hi, how are you doing? In this video, I'm going to talk a little bit about modularity and how the modularity paradigm led us to chiplets. Let's go. So to understand modularity, we don't need to go any further. Just look in the mirror. Human beings are modular systems by default. Think about it. When you were a baby, you learn how to move your arms, right? Arms and legs. Then you learn how to grab stuff. To grab stuff, you need to know how to move your arms, hands, and fingers properly. With the ears, grabbing, punching, pushing, and pulling becomes trivial, right? And you don't think about it. Same as walking. First, you gotta know how to use your legs and feet. Later on, you're just walking here and there and you don't think about it. Our brains developed over the years to make, these mundane tasks very modular and automatic. So your subconscious work with them so you can focus on more important things. That is literally called experience. You will call a professional experienced when a lot of easy and hard tasks are done by him and he doesn't break a sweat. And as engineering is mainly an human activity, I don't know of any other animals trying to do it, except beavers, of course, and a lot of insects. The craft reflects the creator, and engineering itself carries a lot of modularity in order to make things easier to manufacture, easier to test, and of course, easier to use. So with that intro in mind, let's just take a quick look on modularity in the world of electronics, of course, throughout the history. From when electronics didn't even involve silicon and a lot of the other technology you have today, to last year when a lot of crazy things were announced. Well, you saw the title of the video, chiplets. So first of all, components. Electronic components are the very concept of modularity itself. You have resistors and capacitors, inductors. Well, I'm thinking about, before transistors and semiconductors. So you have valves and transformers, motors. If you stop to really think about it, they all follow the same, basic physics laws. Why not manufacture the whole system in just one piece? That'd be a great idea, right? So you go to the manufacturer and ask for a project and they deliver a single component, all the passives, actives, actuators and sensor, everything bottled up in one thing. Well, that would be a really bad idea, First of all, something breaks. You have to change the whole thing. So the first thing on modularity is easy to repair. Second of all, manufacturing that will be a bitch. Modularity helps you in, making the pieces way easier to manufacture. Speaking of, manufacturing, you, the manufacturer, wanna test what you just made. If it's a whole thing, well, it's gonna be a pain in the ass. But if it's a module, you can just make a test stand for the single module, and after all the modules are, tested and approved, you can just bundle them together and test them together and validate the whole design. Way easier. What if you don't want to manufacture all by yourself? Well, modularity allows for many other manufacturers, to manufacture some parts of your design. So you have more sources, and logistically speaking, that's very intelligent. That also increases the speed and capabilities of the manufacturing. So if you have many manufacturers, making the parts of your design, you kind of parallelized your production. Although we know it's not parallel because they are different companies, but still, different components that you can assemble and then, make your electronic circuit design. That's a really great idea, right? So components from the beginning are already very modular. I'm not going back as much as going to, fabric isolators and weird boards, solderless boards. That kind of thing, I'm not going just, especially because a lot of you guys watching my videos are just as young as me. But think about boards and then think about small pieces of that design, small parts of the design that you're gonna use repeatedly, power supply, a sensor kit. You have this template, and you're gonna reproduce that for many different designs or in the same design many times. Why not make board modules? So you can see that in a lot of places. This is as old as falling down. And then it happened, the IC revolution. Suddenly, entire circuits and boards are reduced to the size of a thumb. Quite literally, the first ICs were already super small. Some circuits that were theoretical, or at least you had to build these basic components like op-amps, for example, now they come in a singular package, and you can look at it and understand it as a single component, a single ideal component, not as this theoretical thing that has to be, built up from the scratch, with many discrete components. Now you have this op-amp module, or this clock module, this counter module. ICs, their diversity is insane. I'm not gonna be here citing one by one, but you get the idea. ICs, made this whole hardware modularity thing boom. And then, thanks to calculators manufacturing, some guys in Japan just invented the concept of central processing units as a module. Now you don't have to redesign the entire ASIC, you have some CPUs, memories, and all that's good stuff. And from there, computers, microcontrollers, the thing just explodes in complexity. But CPUs are a great example of modularity in hardware. With these weird things called computers existing, code happened. Software existed before, of course, but now it was everywhere. And with these codes, over the years getting more and more complex and big, and hard to test, hard to maintain, hard to validate. They're getting more complex. They're getting bigger. They were being made by many people. Sometimes the teams were just bigger than just one guy making the code. So how are we gonna make this code thing easier? Well, software modularity. Software engineering is a thing, and to this very day, documentation and modularity is a must if you want your code to work and be easy to develop, to test, and to maintain. Then with recent years, you see another comeback for modular boards, but now I'm not talking about those weird ancient boards of the industry. I'm talking about these modular designs that you see everywhere for breakout boards, evaluation boards, sometimes SIPs, system in packages. They come in these small boards with some already pre-soldered components around them to make the functionalities. You can test and you can put in your board, and a lot of stuff are already working on the go. So I talked about modularity way too much, but I think you get the idea. Modularity is good, make things easy to design, to project, to test, to the other tip of the supply chain, of the pipeline, if you must, of hardware and software design, that is to the client to use, document and test itself if it just damaged a module or not. So modularity is amazing. What it has to do with the topic of this video? Chiplets. Well, I'll be reading off this, really good article from Semiconductor Engineering. I think this site has everything we need on the subjects, but let's take a quick read, and then I'll tell you just, the too long didn't read part of the video. If you want to read everything, links down below, and you can just pause the video right now. But the idea here is, every time you make an IC, an integrated circuit, you have a silicon die in which you have all the circuits inside, Everything is made on the silicon die, and all the rest, which is the very important part of the IC, is the packaging. So make it mechanically and electrically easier to handle and to solder, to mount, etc. The silicon die is made on one go. You have the entire process, and you cannot customize it once you start it. Making silicon chips is really, really complex, and not a coincidence. They only have a few manufacturers in the world, as we saw in the really weird situation of the supply chain in the last 3 years. There are videos out there talking about, chip manufacturing. I'm not gonna go into it, but the important thing is you make a design and you detail everything on the design, and you send to manufacturer, and these foundries basically made silicon chip from the ground up and deliver you the silicon die. You know, this very thin silicon, the circle, most of the time squares, but it's a circle. You know, they make it circular, they reprint, they cut the edges, and then you have silicon die pieces, very fragile, and then you send to a place to, you know, they make the packaging, and then it's more robust and easier to, you know, put on an SMT, you know, SMT line, you know, it's called a surface mount technology line. It's a line in which, you know, you have machines that pick and place. You probably heard about pick and place machines. They pick and place, as their name suggests, the components from trays, put on the board, then goes into an oven. The board heats up, the solder, you know, make everything really tight, really intimate. And then on the other side, it cools down and your board is soldered. That's how all the devices that you're probably watching this video from are made. But there's a catch here. If you caught in my explanation, you need to make this design, this project, check everything, send to the foundry, the manufacturer of the silicon dies, then you make it. There's no in-between steps here. It's done, you decide everything. Once you send it to, you know, to production, it's dealt with. And if you need to make another, usually you have some templates as we have with PCBs, but most of the time there'll be a lot of work changing some specs in your silicon die. And it's here that chiplets come into action. How about, you know, this already tested and validated modules, but instead of system in packages or a system on a chip, you usually have those as well. You have an in-between, you know. You could customize templates, but not on a board level, on a package level, on a silicon die level. And then you can make custom silicon chips way easier, way faster, and, you know, a more interesting approach for the client, because now the client can decide between a lot of options, you know, to have their chip manufactured instead, you know, just some designs. Of course, speaking like that is just, oh yeah, making modular and then make the chips and everything's happy. You have a lot of challenges in that, but that's basically the magic of chiplets. You have modularity down, 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 way down to the silicon die level. So you can have modular parts, hence the name, chiplets, modular parts of the silicon die, and then you could customize them like Lego and make it all work, send it to package, you know, choose the pins, the package you want to use, and there you have it, Bob's your uncle. You also have this, you know, very simple and succinct article on Wikipedia, and you can see here, you know, it names several advantages. I only see 3, but as I said to you, you have modularity as the main thing, and here you have it. Reusable IP, you can use these templates as we call in PCBs. Heterogeneous integration, as I said before, the idea, you know, behind making different components in different places and then assembling in a single electronic circuit design, here applies as well, can make chiplets in different places. And the main thing of modularity, you have a no-go die. What it means is basically you have this silicon die that have been validated, been tested, you know it works, you know it's good. Well, now you just need to integrate them and you have a brand new chip, a brand new design, just by integrating different modules. You must be thinking, how the hell do you integrate them? Okay, chiplets can be made, you know, we make silicon dies, making them smaller or modular is not that big of a challenge. Of course it is, but how do you integrate them is the key part here. And over the last year, you know, since last year, some protocols appeared and become widely known, and I'm going to take a quick look at them. The main ones in this article are UCIe, just similar to PCIe, bunch of wires, I just love this name, OpenHBI and OIFXSR, bunch of, you know, mouthful of letters there. Well, the only protocol to have a proper Wikipedia article is UCIe, and it's the most popular. If you look up chiplets on Google, you'll find a lot of, you know, interesting articles talking about, you know, chiplets and modularity. They all talk about UCIe, and that is because it's, you know, it's a project of really big dogs in the industry. It's co-developed by AMD, ARM, ACE, Google, Intel, Meta, Microsoft, Qualcomm, Samsung, and TSMC. Just those guys, you know. Universal Chiplet Interconnect Express is an open specification for a die-to-die interconnect and serial bus between chiplets. So in the overview part here, it talks about, you know, integration in system on chip, you know, packages that integrate many chips, you know, the same silicon die, and has an entire system. It's like a microcontroller with more peripherals. The ESP32 is a good example, and I know the ESP32 has a system in package as well, but you know, the central chip I'm talking about. And then all the advantages we talked before. Here's the specification, but let's just take a quick look in an article I found in another article from Semiconductors, and they just compare, just have an overview what we know, of course, because people that work in the industry, and that's how I got to know chiplets, they have more information, but it's not publicly yet. Again, thanks for Semiconductor Engineering, great article here. So it talks about UCIe and discusses the, you know, the difference between you have system on a chip and system in package, and then, you know, chiplets are kind of in between those two. But the important part here about the protocols is this image, this really small image. Well, sorry if you're watching this on computer, this image is not as high quality as expected, but here you can see the many protocols we saw in the Wikipedia article discussing the XRR, bunch of wires, the UCIe, and now you have, you know, other protocols in here as well, the AIB from Chips Alliance. And you can see the data rates, gigabit per second to me is already a lot, but you know, we're talking about inter-chip connect, so you really need a really high data throughputs, and you have, you know, some units to tens of gigabits per second, and XRR here proposes hundreds of gigabits per second. Protocol not defined to a lot of them. This article is not, you know, super new, but UCIe has already, you know, a definition. Oh, the others have already definition as well, but you know, see here it says UCIe is basically PCIe for chips. And you can see the packages, which in you can use, you know, the protocols and target applications. And for those who still hadn't caught the idea of chiplets, here you have this pretty, let me just get a quick zoom in here. You have this image here to show basically the idea behind. You have a protocol and then chips. The protocol is, you know, you have the physical layer really well detailed. This is really important, but all the details are here. You just basically connect them to this bus, and the chips will talk between themselves. Of course, you need faster protocols between, you know, if you're gonna make CPUs modular and memory modular and all that, but you can use more flexible and easier to manufacture protocols if you want, you know, talk to peripherals and all that, unless you're going for a more specific application chip. I know chiplets are not new to the industry. I just wanted to make this video about chiplets, just, you know, to enunciate, to make it very clear that modularity is a must in an industry that, you know, aims at integration and smaller sizes and lots and lots of features, especially now with, you know, human-machine interfaces having AI, computer vision and all that. We need more and more modularity, and with this system getting more and more complex, your software better as well have a lot of modularity indeed. I really hope you guys found this video, you know, interesting. I hope you learned something, and share ideas in the comment section down below. I love when you people comment on my videos, and I will see you in the next video. Bye bye.